Welcome to the final module of Grade 12 Artificial Intelligence. In Part A, you framed a real problem and designed a solution. Now, in Part B, you build it. You evaluate it honestly against the criteria you set. You deploy a working demonstration, and you defend the whole thesis. This is where a design becomes a finished working piece of artificial intelligence. Here is our plan for the lesson. We'll move from a design to a working build, then implement and iterate toward our target. We'll evaluate the result honestly against the success criteria we set in advance. We'll deploy a small demonstration and document the work so others can trust it. We'll measure real impact and write the thesis report. And finally, we'll defend it, reflect, and look back over the whole year. Building begins by rereading your Part A design, because the design is the promise the build must keep. Resist the urge to build everything at once. Make the smallest version that runs end to end, from a maize-leaf photo all the way to a predicted label, even if it is rough. Start from a strong, simple baseline rather than the fanciest model, so you have something honest to beat. Put your work under version control so every change can be traced and undone. And build the data pipeline before the model, because a model is only as good as the data feeding it. With a skeleton running, the real work is to improve it. Good implementation is a loop, not a single leap. First, split your data into 3 parts: a training set to learn from, a validation set to tune on, and a test set you lock away until the very end. Track every experiment. Write down what you changed and what it scored, so improvement is evidence, not memory. Tune on the validation set and never touch the test set early, or you fool yourself about how well you will really do. Diagnose your errors by looking closely at the photos the model gets wrong, because they tell you what to fix next. And know when to stop, when more effort no longer moves the metric. Then it is time to judge the result against the bar you set. Evaluation answers one honest question: did the build meet the targets you set in advance? In Part A, you wrote down success criteria, so now you compare each measured result against its target. Accuracy reached 91%, above the 85% target, so that criterion passes. But recall on diseased leaves came in at 88%, just below the 90% target. That one misses, and it matters most because a missed disease is the costly error for a farmer. Latency on the phone comfortably passes. Choose metrics that match the real goal, report them against pre-stated targets, and let the evidence speak even when it is not all good news. A model that lives only on your laptop is not yet a solution. Wrap it in a simple demonstration. A farmer takes a photo and a label comes back. Make the work reproducible. Share the code, record which version of the data you used, and fix the random seed, so another person gets the same result you did. Write a model card that states plainly what the model does and where it should not be trusted. Note the real deployment context. In this case, a low-end phone, often used offline in the field. And plan to monitor it after release, because a model can quietly drift as conditions change. With a demo that runs and a record others can follow, you can ask what difference it makes. A thesis is judged on its impact and how clearly you report it. Open with a clear claim, then give the evidence behind it. Measure impact in human terms, not only in numbers. For our detector, that might be diseased plants caught a week earlier and a harvest saved for a Rwandan family. Be honest about limitations and about who your data might leave out, such as crops or lighting it never saw. Structure the report so a reader can follow the whole journey: the problem, the design, the build, the results, and your reflection. And cite every dataset, tool, and source you relied on honestly. A well-written report is what lets your work be trusted and defended. Finally, you defend the work. A strong defense does not hide from hard questions, it welcomes them. Know your own weaknesses before the examiner finds them, and you will never be caught off guard. Answer with evidence from your results, and when you genuinely do not know, say so plainly, because honesty is more convincing than a guess. Separate clearly what you proved from what you merely assumed. Reflect openly on what you would do differently with more time or more data. And look ahead to the next experiment your work invites, because good research opens new questions. Defending well is the mark of a real AI practitioner. Before we close the course, let's see the whole year as one map. You began with learning agents and reinforcement learning, then opened up large language models and the scaling laws behind them. You studied AI safety and the frontier of agentic systems. You connected AI to global development and learned the research methods that make findings trustworthy. You explored governance and policy and how an AI idea becomes a responsible business. You placed it all within Rwanda's Vision 2050 and its AI strategy, and met generative and multimodal models. And across these final two modules, you designed, built, and defended a senior thesis of your own. 12 topics, one journey from theory to a working solution. Capstone AI is not a classroom toy. Evaluated honestly, it reaches real decisions. In Rwanda, a crop disease detector like ours can help a smallholder farmer act before a field is lost. A Kinyarwanda health helpline can triage common questions and point people to care. In the International Baccalaureate, an extended essay might model flooding risk for a town in England. In a United States capstone, a student classifier might flag unsafe road crossings near a school. Across every system, the same discipline holds. It is honest evaluation that decides what we can trust and what we must not. A few traps weaken even a clever solution, so let's name them. First, testing on the same data you trained on. The scores look wonderful and they mean nothing. Second, choosing your metric after you see the result, which is just flattering yourself. Set the criteria first. Third, reporting a single accuracy number while hiding the cases that fail, especially the costly ones. Fourth, a demonstration that no one else can reproduce, which leaves the result unproven. And fifth, defending by hiding your limitations, when owning them is what earns trust. Avoid these 5 and your thesis will stand. Let's gather today's key ideas. Build the smallest version that runs end to end, then iterate in measured loops. Split your data, tune on the validation set, and lock the test set until the end. Evaluate against criteria you set before you tested. Deploy a reproducible demonstration with a model card that states its limits. Report a clear claim backed by evidence and measure impact in human terms. And defend honestly. Own your limitations and separate what you proved from what you assumed. Now let's check these ideas with 3 quick questions. Here is the first question. Your model scores 99% on the very data it trained on. Is that a valid evaluation? No. A model can simply memorize the data it has already seen. So a high training score proves nothing about new cases. A valid evaluation uses a held-out test set the model has never seen. Question 2. You release the crop disease detector to farmers. What should you set up to catch it failing over time? Monitoring. The real world drifts. New crops, new phones, new lighting, and a model that was accurate at launch can quietly degrade. Monitoring its live accuracy after release lets you catch that decline early. Last question. During your defense, you are asked about a weakness you know is real. What is the best response? Acknowledge it honestly and explain how much it affects your conclusions. Hiding a known limitation destroys trust the moment it is uncovered, while owning it and bounding its impact is exactly what a strong defense does. Congratulations! You have reached the end of Grade 12 Artificial Intelligence. From learning agents and large language models through safety, governance, and global development, to a senior thesis you designed, built, evaluated, and defended yourself, you have come an extraordinary distance. You no longer only study artificial intelligence, you can create it, judge it honestly, and stand behind your work. Carry that honesty and that curiosity into whatever you build next, and use it to serve the people around you. It has been a privilege to learn alongside you. Be proud of how far you have come, and keep building the future. Well done.